We're asked to determine the sine of 135 degrees, the cosine of 135 degrees, and tangent of 135 degrees. So let's start off just by drawing a 135 degree angle in standard position. So to do that, let me draw some axes, and I'll also put a unit circle on that axis. So that's about as good as I can hand draw a unit circle. And let me mark these up, mark it up a little bit neater. So this is when x is equal to 1. This is when y is equal to 1. This is when y is equal to -1, and then, sorry, this is when x is equal to -1, and then this is when y is equal to -1. And the only reason why I have drawn it as kind of a dotted line is I just found it easier to freehand a dotted line. We can fill it in. It actually should be a filled in line. So there you go. There you go. All right. Now let's draw a 135 degree angle in standard position. So let's sit the vertex of that angle at the origin. We do this in a new color. So it's going to sit at the origin. The initial side is going to go along the positive x-axis. So just like that. Draw it as a ray. And then the terminal side, since it's a positive 135 degrees, we're going to go in a counterclockwise direction. If we go straight up to the y-axis, that gives us 90 degrees. We need to get to 135, so we have to go another 45. So we have to go another 45. Takes us right about halfway, or exactly halfway through the second quadrant. So it takes us right over there. Right over there. So that is a 135 degree angle. Now, we know from the unit circle definition of trig functions that the intersection between the terminal side and the unit circle is going to have some coordinates, x, y. We know from the unit circle definition that x is equal to the cosine of 135 degrees in this case, and y is going to equal the sine of 135 degrees. And we know that y over x is going to be equal to the tangent of 135 degrees. So if we can figure out this intersection point, the x and y coordinates, we've essentially figured out this entire problem. And as a little bit of a hint, what I'm going to do is create a triangle here. And this really does show the connection that shows that the unit circle definition is really just an extension of the traditional SOHCAHTOA right triangle definition. So what I'm going to do is I'm going to create a right triangle here. Let me do it in a different color, color different from my unit circle. So I'm going to drop a right triangle here. So that's 90 degrees. This magenta line has gone straight down. And if we can figure out the base, if we can figure out this distance right over here, let me do this in a different color. If we can figure out this blue distance, we know that it's in the negative direction. So if this blue distance is whatever it might be, the negative value of that, because we're going to the left of the origin, is going to be our x-coordinate. And whatever this height is here in magenta, that's going to be our y-coordinate. You see it right over here. So the x-coordinate is right wherever this blue distance takes us to the left. And the height in magenta is our y-coordinate. You see it right like that. So let's think about what we know about this triangle right over here. So my first question to you is, what is the length of the hypotenuse of this triangle right over here, the one that's formed between these points? The origin, the intersection between the unit circle and the terminal side of the angle, and where this vertical line intersects the x-axis. So these 3 points right over here. What is the hypotenuse of the right triangle formed by those 3 points? Well, this hypotenuse right over here, just this distance right over here, it is a radius. It is the length of the radius of the unit circle. And by definition, the unit circle has radius of length 1. So the hypotenuse here has length 1. Now, my second question to you is, can you figure out the angles of this triangle? And in particular, can you figure out the measure of this orange angle right over there? Well, let's think about it. It is essentially, or it definitely is, supplementary to this 135 degrees. 135 plus this orange angle must be equal to 180 degrees. So 180 minus 135 gives us a 45 degrees. And this is often referred to as the reference angle. It's that positive angle between the terminal side of an angle, whether that 135-degree angle, and the x-axis. So that's 45-degree angle right over there. Now my next question to you is, can you figure out the last angle in this triangle? We know that this one is a right angle. We know this is 45 degrees. Can you figure out what this top angle is right over here? Well, we know that the angles in a triangle have to add up to 180 degrees. So if you call this angle theta, we know that theta plus 45 degrees plus 90 degrees, because we have 90 degrees right over here, this right angle, must add up to 180 degrees. Or theta plus 135 must add up to 180. If you subtract 135 from both sides, you get theta is equal to 45 degrees. So this is also 45 degrees. Theta is also 45 degrees. And let me zoom in on this triangle because it's getting a little bit messy. So let me zoom in. So this is the exact same triangle. I'm just going to blow it up, and I'm going to try to do it the same colors. Same colors. And then that was kind of a greenish color. So let me draw it like that. There you go. So this is just a zoomed in version of the same triangle. This right over here is a right angle. We know that the hypotenuse has length 1. It's opposite the right angle. We know that this angle right over here is 45 degrees. And we know that this angle up here is 45 degrees. So my next question to you is, can we figure out the length of these sides? And the first thing, well, I'll let you think about that for a second. The first thing you might realize from your traditional geometry is that this is a triangle that has two angles that are the same. And if the two angles are the same, then the sides right here are going to be the same as well. So we know from our geometry that this side is equal to that side. Sometimes it's easier to visualize. If you have a triangle that's like this, and these two base angles are congruent, then you know that these two sides are congruent. This is one of the fundamental things that we learned in geometry. And so this is just reoriented in a different way. So we know those two sides are going to be the same thing. And what you're going to eventually realize, we can figure this out, but you're eventually going to realize that triangles like this, 45, 45, 90 triangles, we're going to use the Pythagorean theorem this time, but these are good triangles in general to know the ratio. You know that the two of the sides are going to be equal, and the ratio between them and the hypotenuse. But we'll figure it out this time. So we can use the Pythagorean theorem. We know that this is x, or we could call that x. We could call that, actually let me not call them x, because I don't want you to confuse that x with this x. So let me just call, this could be a, and this could be a as well, or they're definitely going to be the same because the base angles are the same. So we can use the Pythagorean theorem. So using the Pythagorean theorem, what do we get for the value of a? Well, Pythagorean theorem, we have a squared, this a squared, plus that a squared, must be equal to the hypotenuse squared, which is just 1 squared. Or we get 2a squared is equal to 1. Or divide both sides by 2, you get a squared is equal to 1/2. Or take the square root of both sides, you get a is equal to 1 over the square root of 2. And if you want to rationalize the denominator, you can multiply by the square root of 2 over the square root of 2, not changing the value. So this gives you square root of 2 over square root of 2 times square root of 2 is just 2. So a, or the side of this thing, is equal to square root of 2 over 2, and this is equal to square root of 2 over 2. Now let's get back to the fundamental question. What is the cosine of 135 degrees going to be equal to? Well, let's remember that's going to be equal to the x-coordinate. The x-coordinate is, we're essentially going this distance to the left of the origin. So the x-coordinate right over here, the x-coordinate is going, you might say, oh, maybe it's square root of 2 over 2, but x being square root of 2 over 2 would get you over here. To be over here, you have to go negative square root of 2 over 2. So the x-coordinate is equal to negative square root of 2 over 2. So cosine of 135 degrees is equal to negative square root of 2 over 2. Now what's the sine of 135 degrees? Well, we already established that's the y-coordinate, and the y-coordinate literally is just the height of this magenta side, just the height of this magenta side, and we just figured out that that is square root of 2 over 2. So y is equal to, so this point right over here, this point right over here is square root of 2 over 2. So y is equal to square root of 2. This y value is square root of 2 over 2. And so sine of 135 degrees is square root of 2 over 2. So I can rewrite this coordinate here as the x value is negative square root of 2 over 2, and the y value is positive square root of 2 over 2. So I can write that. I now know the x and y values of that intersection point. And so my final question for you, and then we are done, is what is the tangent of 135 degrees? Well, we know it's just the y value over the x value, so that's going to be equal to, the y value is square root of 2 over 2, square root of 2 over 2, and then the x value is negative square root of 2 over 2. Negative square root of 2 over 2, and so this is going to be equal to, and we're at the home stretch now, it's going to be equal to square root of 2 over 2 times the reciprocal of what's in the denominator, so times negative 2 over the square root of 2. Well, that cancels with that, and then you're just left with a negative 1. So this all simplifies to negative 1. So the tangent of 135 degrees is negative 1.